Hi, I'm Jackaway. I'm sitting here out in front of the New York Public Library where it's a balmy 88 degrees Fahrenheit or 30 degrees centigrade. It's pretty hot, but temperature isn't something we normally consider to be relative. But space and time are? What do you mean by that? Let's go take a look.
1 minute, 44 seconds, downrange 7 miles, 12 miles high.
Since its publishing in 1905, special relativity has been the cornerstone of theoretical physics, but it's really just based on one or two key principles. The first is that the laws of physics are the same no matter one's point of view, or reference frame, as we like to call it. And that might not even sound like a big deal or a surprise, but it actually is when we come to think about what it means.
Directly following from the first concept is another, which states that the speed of light is always exactly the same, and that it doesn't vary based on whether or not you're moving. Think about it, if it did, that would be a change in laws of physics due to one's own reference frame, and we can't have that. For example, if this car here were to turn on its headlights, both an observer standing where I am and the driver of the car would observe that light wave to be traveling forward at exactly the speed of light. No surprises there. But if the car started to drive away, I would continue to see that light moving at the speed of light, but the driver would too, even if we might think he'd see it moving a little bit slower.
That seems ridiculous, counterintuitive, but experiments really do show that the speed of light is always exactly the same.
Now, just for the sake of argument, let's say that that car was secretly a Tesla Roadster the whole time, and Elon Musk sends it to the nearest star to us, Proxima Centauri, at half the speed of light, just because he felt like it. From the reference frame of someone back on Earth, the light emitted from the Roadster would take a total of 4¼ years to reach Proxima Centauri. But from the reference frame of someone aboard the Roadster, Proxima Centauri is rushing towards them at half the speed of light. Therefore, any light they emit will reach the destination much faster. Well, but wait, we're talking about the same event, the light from the Roadster reaching Proxima Centauri. The only conclusion we can come to is that an observer aboard the Roadster would literally experience and observe less time taking place than an observer back on Earth due to the fact that they are moving.
That's pretty incredible, and that's what people are talking about when they say space and time are relative. Now, how does that affect us in our everyday lives? Well, not much, because we're never traveling very close to the speed of light.
And in fact, even at the low velocity of a GPS satellite, when super precise timing mechanisms are required, you can't do it without relativity.
But I think it's still pretty cool to know about. This has been Relativity in 3 minutes or less. Thanks for watching.